This is an ellipsoid. It's a round shape, sort of stone-shaped. We can see when we cut it on ZX plane, we get an ellipse. And likewise, when we cut it in the YZ plane, we also get an ellipse. And finally, when we cut it horizontally, we also get an ellipse. Therefore, for an ellipsoid, all traces are ellipses. The equation for an ellipsoid is x squared over a constant a squared plus y squared over a constant b squared plus z squared over a constant c squared equals 1. So we can connect this into a sphere, which is x squared plus y squared plus z squared equals r squared, in the same way that we can connect the equation of an ellipse, which is x squared over a squared plus y squared over b squared equals 1, to that of a circle. So if we have a circle, say x squared plus y squared equals 4, we can get some values. 0, 2, 2, 0, square root of 2, square root of 2, 1, square root of 3, for example. And when we draw it, we know that the y-intercepts are 2 and negative 2, and the x-intercepts are also 2 and negative 2. So, if we were to divide the x value by some constant, x squared over 2, let's say, we need greater values of y to still result in 4. So we still have something like 0, 2, because 0 plus 4 equals 4. However, if we put 2 in, we're going to get 4 over 2, which is 2. And therefore we'll need square root of 2, not 0. Likewise, if we put in square root of 2, we get 1, and then need square root of 3. If we put in 1, we get 1/2, and need square root of 7/2. And if we have 0 for y, we'll get that x squared equals 4 times 2, so x squared equals 8, so x is going to equal square root of 8. So now our shape is going to have 2 and negative 2 on the x-axis, and for their y-intercept, square root of 8 and negative square root of 8, which gives us this stretch shape for an ellipse. In the same way, if we took a sphere, if we divide any of the values by a constant, it necessitates that the others must be larger. So if x squared, if a squared is larger than y squared and z squared, it gets stretched in those directions. This is an elliptic paraboloid. if we cut it in the xy plane, we get an ellipse, or in this case, more like a circle. If we cut it in the xz plane, we get a parabola. And likewise, if we cut it in the zy plane, we also get a parabola. Therefore, the horizontal trace of an elliptic paraboloid is an ellipse, and the vertical traces are parabolas. The equation for an elliptic paraboloid is x squared over a squared plus y squared over b squared equals z over c. So the first thing that we notice is that z is not squared, which means that all values are going to be positive for z, meaning everything is going to be above the xy plane equals 0. So breaking down the parts of an elliptic paraboloid allows us to understand how its components are working to make the traces. So considering z as a constant and just looking at the x and y variables, we can see that it's essentially the equation of an ellipse. And therefore, we can understand how the horizontal traces, the ones in the xy planes, are ellipses. So considering x or y a constant gives us an equation something like this: x squared over a squared plus, let's define the constant k as y squared over b squared times a squared, so that we can say k over a squared equals z over c. Now we can move a squared and we get x squared plus k equals a squared over c times z. And then we can see that this is essentially the equation of a parabola, which is z equals some quadratic equation, x squared plus ax squared plus bx plus c. And we can move all of that back from the z and say that x squared times c over a squared plus a squared over c over a squared times k equals z. So this would be our a, and this would be our c. And the same, because we can see in the symmetry of the equation that the same would be if we considered x. This is a hyperboloid of one sheet. We can see that the horizontal traces are ellipses, and that the vertical ellipses are parabolas opening sideways. It's sort of an hourglass-like shape in a way, though less angular, like the cone, has a larger opening in the middle. This is a hyperboloid. The equation for a hyperboloid of one sheet is x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. So again, by splitting this into its components, you can see how its traces work. So we can see how eliminating the z value as a constant gives us equals 1 plus c squared over c squared. And considering this as a constant, we can see that this is the equation of an ellipse. Eliminating the x or y variable, we can see and this is all just a constant, we can see that we get the equation for hyperbola. And the same if we eliminate y as a variable. And therefore, for the hyperboloid of one sheet, we're going to get a shape with horizontal traces that are ellipses and vertical ones oriented in the x or y direction that are hyperbolas. This is a hyperboloid of two sheets. We can see that the horizontal traces are ellipses, and when we cut along the z-y axis, we can see that we get a hyperbola as our trace. And when we cut along the zy, we see that we also get a hyperbola. And therefore, for a hyperboloid of two sheets, we have horizontal traces that are ellipses, vertical traces that are hyperbolas opening upwards and downwards. And there are two sheets. The equation for a hyperboloid of two sheets is negative x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. So this one's a little bit more difficult to conceptualize. When we make our z 0, our equation is invalid because two negative values cannot make a positive value. However, if we make z greater than c, say 2 times greater, we get negative x squared over a squared equals y squared over b squared plus 2 equals 1. And moving 2 over, we get equals negative 1, which is now valid. So in the same way, if z is less than negative c, we will also be able to shift the equation in the same way to make it valid and equal 1. So we can see here that this shows how we need to have values greater than or less than c to be valid and equal, which is where we get our shape of a hyperboloid of two sheets, which looks something like that. And if we eliminate the negative signs, we divide everything by negative 1, we can see that we get the equation for an ellipse. And therefore, the horizontal traces are going to be ellipses. So if we're going to now call either x or y a constant, we get z squared over c squared minus x squared over a squared equals 1 plus y squared over b squared. And this is some constant, and we can see that we get the equation for a hyperbola. And likewise, if we do z squared over c squared minus y squared over b squared, get 1 plus x squared over a squared, which is also a constant and is also a hyperbola. Will look something like this. And therefore, the traces in the xz plane will not be parabolas, but will be lines, triangles, when y equals 0. And this will happen too if x equals y, or x is any value related to y. And therefore, as we go around the cone radially, we will get these same traces as we slice it, either when upon the line x equals y, y equals 0, or x equals 0. However, when y is merely a constant that is not 0, or x is a constant that is not 0, we're going to get the equation of a parabola. Times c equals z. So while on looking from the top, the x and y axis, we're going to get traces that look like this. Further along, we're going to get traces that look like that, with pairs of parabolas flipped. This is a cone. You can see, turning it around, and it's symmetrical. So I'm going to just deal with the bottom for now. So if one were to cut in the xy plane, one would find that the horizontal traces are ellipses. Now, if one was going to cut in the zx direction, if one cut directly on the axis, one would see that we get triangles. And if we had the whole cone, we'd see that we get some shape like an X for them. And now, but if we don't cut on X, or as we can see, Y equals 0, and we instead cut on another one, we can see that we get parabolas. And if we have both, the traces look like this. So therefore, for a cone, the horizontal traces are ellipses, the vertical traces are parabolas, and if x or y equals 0, they're triangles. A hyperbolic paraboloid is a surface, so I'm going to take a slightly different approach at showing the traces. So it has a parabola opening upwards in the ZY direction, which means it's going to look something like that from that angle. It is a hyperboloid in this direction. In the XY plane.